Hi, everybody. This is our finite element analysis project progress report for our torsion spring. I'm Alex Blakely.
I'm Finley Butler.
I'm Mary Brownell.
And just a quick reintroduction of the system. We're doing our senior design project, which is a spring-loaded dampening hinge, which is sponsored by Intel. And this is a self-contained hinge system, which we are designing for a server door. Basically gives it a self-opening feature and dampens the vibrations of closing the door when maintenance is working on it. It's very small. It's only 14 millimeters in length. And we wanted to choose this system because to apply to a real world situation, and it's also going to help out our project quite a bit. It has fairly simple, straightforward components. And we're focusing on the torsion spring as that's what's undergoing a lot of the cyclical loading. And we're going to use this to work on some of our finite element analysis skills.
The pre-processing phase is made up of 6 parts: identification of external and internal forces, discretization into finite elements and nodes, assuming a shape function to represent behavior, developing equations for an element, constructing a global stiffness matrix, and applying the boundary conditions and initial conditions in loading.
So to begin our analysis, we had to do an actual setup for the model and make a bunch of assumptions. And so our hinge is basically 3 springs laid out into onto 2 solid hinge pieces. And so some of the assumptions that we made was that the center of the torsion springs held in place as stationary. And so that's going to be one of the boundary conditions that we had to consider. And that'll be our second node. So the first node's at the top, second node's in the middle. And then the springs, we're also assuming, which they are, all the same material. They all have the same leg length, cross-sectional area, and the distance between all 3 of them is also equal. And then the force is also exclusively applied in the form of the door for the server on the top part of the hinge. And so that's where all the deformation is going to be, is on the top half of that spring. And so during the discretization, we basically combined the top and bottom 3 springs into a single element. And so you can see from a model to the left, we have 3 nodes and 2 elements. And we believe that since the element is the 3 springs, that we could do that. And so we also divided the spring itself into 2 halves, since it'll basically be reacting differently on the top than it was on the bottom. And that 90-degree deflection that will happen on the torsion spring is when the server door will be opening and closing. And like I said before, the bottom leg is going to be staying still. So we're basically saying that that's fixed, especially in terms of our ANSYS simulation. And during this, since it's a spring and we're worried about deflection, Hooke's law, this form that we have there, K equals AE over L, is going to be the governing equation. And those 2 equations there is just the combination of the spring legs, as I noted before. And so for the pre-processing, we we used the static equilibrium based off of the model that we had, and we made equations up for all 3 nodes. And so you can see at the top, middle, and bottom. And then we use those nodes to create matrix, or to create a matrix for each node. And then using the equation at the bottom, we're trying to get the global matrix by combining all 3 out. And then after we get the global matrix, we apply the boundary conditions, and that gave us the matrices we can use to find the stress or average stress and the deformation.
And this is the pre-processing solution, and those nodal equations that Alex mentioned are there at the top, and those accumulate into the global matrix and applied to find the maximum deformation at 0.0143 meters. And this pre-processing solution is important because it can help us verify our calculated computational analysis on ANSYS. So yeah, that's just the work on our pre-processing solution.
The next steps of this project include creating an ANSYS simulation model, creating a physical geometry of the spring using space claim, ensuring that the material geometry and forces are accurate, calculating the deformation and average stress, and using stress concentrations for project application.
And this is our preliminary ANSYS model. In space claim, we basically just made the coil and then extruded for each of those spring sides, and all of our dimensions were taken off of Lee's spring. That's where we got our stock spring from. And this is going to work into ANSYS much better than Inventor, where we were kind of struggling on getting the spring to operate correctly. And that's everything. If you have any questions, reach out. Thank you.